Okay, so um, I finally got around to testing out some of the multiprocessing stuff, and the really tricky bit was figuring out how to manage memory, specifically how to deal with shared memory. So this was one of my first tests where I actually had shared memory for the positions and velocities for a bunch of particles. In the preview that you're seeing here, sorry about the focus keeps going in and out, but in the preview that you're seeing here, this is, I think, 10,000 particles, and we're currently running everything on a single process, just the main process like normal. It's not very fast, it's pretty slow. You'll see in a moment here, because then we switched to having two processes, which is the main process and another process which handles the update for the particles. And unsurprisingly, that it's about the same amount of time per update. It's basically just like running it on a single process anyway. The really noticeable change is when we switch to having two processes performing updates on the particles. I'm also having a sleep happening between each of these tests so that we can see on the graphs on the right there when a test has started and ended approximately. This part of the testing was kind of excruciating, honestly. This was very slow. I'm going to speed this up again in a second here, actually. But yeah, so what I'm doing right now is I'm incrementing. I keep increasing the number of processes that are being used. I think it went like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then it jumped to 24, and then last was 36. Just the 24 and 36 were just to see what would happen. But yeah. I've got all of the data that we've shown here charted out at the end, so you'll get to that. We'll get to that when we get to it. The important thing here is that right now, during this particular test, I had it so that when an update was being performed on a particle, it would have to look up the memory address, or the memory, it'd have to index the memory dynamically, I suppose, every single time. And I thought, well, maybe that's not the best way to do it. So in this second test, instead, what I did was I had it so that it would have each process, it would have the shared memory already loaded into that process ahead of time. And you can see already, especially compared to that first test, this is still just running on the main process right now. There's just one process, but it's already faster because it's not dynamically having to look up that memory. It's already been looked up. I think we got like 3 times speed increase just from that. And of course, doing it with just a main process and one process performing the update, again, there's no real noticeable change. Then I tried 2 processes, of course, and again, it's just like, whoa, that's already a big improvement, especially compared to the very first test I did. That's actually acceptable speed. Like if that were a game, that would be relatively playable. And of course, I do more tests. I do 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Obviously, because we're having to set up each of these processes with every single shared portion of memory for every particle, the setup time is increased during this version. But the consequence of this is that we end up with much, much, much faster run times. Yeah, that was like a big leap right there. Just doing that, just switching from dynamically looking up the memory to having it already looked up. That made a big difference by itself. And then, of course, the addition of having multiple processes performing updates on the particles, that also increased the speed of the simulations, which is just great. It's good news. This experiment was super, super important to make sure that I was doing this right. And I mean, this is going to be like the base of the simulations that I'm going to be building from here on out. I just want to make sure that I'm doing it right to begin with, because if I'm building on a foundation that's not very strong, it's not going to be worth it. I'm going to have to start over again probably. Anyway, it looks like we're reaching the end of this. This is the 32 processes one, and you can see it takes a while to set up each of those processes. But yeah, look at that speed. That's not bad. It's doing 50 updates each time it does this test, and then it just finds the average time of each of those updates. And then so you can see at the end here, we've plotted the data of these results. So the blue one there was the first portion that we did, where we were dynamically looking up those particles in memory. And obviously that's quite slow. And you can see that the first two values there, it's pretty much just a straight flat line. But then immediately after that, it just dips down very quickly. And then there's diminishing returns as we add more and more processes, because there's a limited number of cores. And I mean, it's to be expected. You're essentially taking a number and dividing it by another number, and even if you keep increasing that number that you're dividing by, the divisor or whatever it's called, yeah, you'd have to do like powers of 2 or something for it to be noticeable. It's kind of like the issue with the resolution of screens. Like people switch from 4K to 8K and say, oh, there's not really a whole lot of difference. And even though there's significantly more pixels, the reason why it's less noticeable is because of diminishing returns. This is boring, so I'm just going to wrap this up. This is a good test. I think my butter zone for this from here on out is going to be about 8 processes. And I want to make sure that I have each of my processes set up from the very beginning so that there's minimal lookup and there's minimal communication between the main process and any of the other processes. At least that's my theory. Okay, thank you for watching. Have a good day.